Hi everyone, welcome to 7Places Introduction to Chemistry and Cookies, Day 1. I'm Amanda and I'm super excited to be teaching you guys today. So welcome to your first day of chemistry. What we're going to be doing today is exploring the tiny world of atoms, unlocking the secrets of the periodic table, learning why the noble gases are cool, working magic with a paper and pencil, and of course connecting all of this to cookies because both cookies and chemistry are awesome. Here is just a little poster. It says science, it's like magic but real, and that's something that I certainly believe, and hopefully after this you guys will too. So we're gonna just skip the icebreaker, but if you want to introduce yourself, feel free to tell us your name and what your perfect cookie would be like in the comments. Also, Albert Einstein once said, the important thing is to not stop questioning. So if you don't understand something, please just ask. Of course, if you're in one of our live camps, you can just ask your instructor, but here you can leave your question in the comments and I will do my best to answer them. So what exactly is chemistry? This is probably something important to establish before we start learning about it. Well, chemistry is basically the properties of matter and its interaction with energy. Now, matter is the stuff all around us. Basically, everything that you can see and have ever seen is just made up of matter. Matter is just what we would call stuff. And energy is also important because all matter has energy, even if it's very small amounts. And the way that matter interacts with other matter and how energy influences this is a huge, it plays a huge role in our lives. From, the smallest chemical reactions to things that happen every day. If you ask me, it is kind of like magic, again, and hopefully, you'll see that as well as we go further on. How does chemistry apply in real life? Well, we're talking about chemistry, we're talking about tiny atoms, tiny molecules, and sometimes it's easy to wonder, why bother learning this at all if it's so small? But chemistry actually affects us every day. So for example, every time you burn something, every time you light a candle, chemical reactions are taking place. Every time you breathe in, you can thank plants for photosynthesis. And, photosynthesis is just chemical reactions, and that gives us energy from the plants that we eat, and that gives us oxygen, which we need to breathe. So, very useful chemical reaction right there. Every time you digest something, chemical reactions are happening. Chemical reactions are happening all of the time inside of you and me, as we speak. So that's fascinating. Then also a lot of baking and cooking, there's chemical reactions taking place. Sometimes when you combine two ingredients and when you add heat to it, chemical reactions again. And there's countless other applications in medicine, in transport, in technology. So chemistry is really everywhere. And by seeing how these tiny atoms and molecules interact with each other on, a molecular basis, then we can actually see how, bigger matter interacts with each other as well. So it's really important. So first, we're just going to get into let me just get a laser pointer, there you go, into the very basics of chemistry, the fundamental stuff, so then we can start building on that. And the first thing we're going to talk about is atoms. Atoms are what we call the building blocks of matter. And again, if matter is just all stuff, me, you, air, grass, earth, if everything is made of matter and atoms make up matter, then, we could say that everything is made up of atoms. Atoms are extremely small. We certainly can't see them without some very in-depth technology. And all atoms are made up of 3 different subatomic particles. Now we call them subatomic because you can see the word atomic here, so that has to do with atoms, and then sub because it's kind of like a smaller part of them. So there's 3 different types. We have the protons, which have a positive charge. We have the neutrons, which have a neutral charge. They just have no charge. 0. And then we have the electrons, which have a negative charge. So as you can see, this is actually just a very oversimplified kind of diagram of an atom. So we have all the protons and neutrons kind of clumped together right here in the middle. We call that the nucleus. And again, since it has positive protons and neutrons, which don't have any charge, the kind of overall charge of the nucleus is positive, right? Because if you have a lot of positive charges and then something that doesn't affect anything, like charge-wise, then the nucleus is going to be have a positive charge. And then around the nucleus, in what we call an electron cloud, it's basically just a fancy way to describe this space, are the electrons. And remember, those are negative, so the electron cloud is going to have a negative charge because it has the negative electrons in it. And what happens is that these electrons are kind of spinning around the nucleus like this. They're just, continually circling it because the positive protons and the negative electrons attract each other. If you've ever heard of the phrase opposites attract, this certainly applies here because the positive charge of the protons and the negative charge of the electrons attract each other. So again, we have the protons and neutrons in the middle and the electrons circling around it in the electron cloud, and which are attracted by the positive nucleus and the positive protons in the nucleus. All right, so that's all very interesting, but how does that, how can we build on that? Well, after atoms comes elements. An element is basically just a substance that can't be broken down into simpler substances. So, if you grab a pure sample of an element and you start looking at it really, really closely, it's made up of atoms, of course, but you can't kind of separate it into other substances. So, for example, if I were to grab pond water or something, and we look really closely at it, well, we have water, but we also have some bacteria. We might also have some sort of, salts, maybe some sort of chemicals, hopefully not, but, it could happen. So we can kind of break that down into other substances. It's not just pond water, it's made up of things, but elements are just made up of themselves. There's no way to kind of break them down. When you try to break down an element, all you're gonna find are just atoms of that element. So they're made up of atoms with the same numbers of protons, electrons, and neutrons. So basically every element has like its own type of atom, and we kind of see what type of element an atom is by, again, looking at the numbers of the subatomic particles. So, and every element is its own type of atom, as I've said before. So for example, let's take hydrogen, right? Here we have hydrogen, you can read. And then we have a number 1 here, which basically means, well, we'll get into reading the periodic table in a bit, but every atom of hydrogen has 1 proton, 1 neutron, and 1 electron. So we can see here the nucleus, and here we're gonna have 1 positive proton and 1 neutral neutron. And then around it, we have 1 negative electron. And every atom with 1 proton, 1 neutron, and 1 electron is a hydrogen atom. Of course, this is a bit of an oversimplification, but generally for this class, we're just gonna kind of go off of that. And now we get into molecules and compounds. So, okay, well, if atoms make up elements and elements can't be subdivided, what do elements make up? That's a good question. And elements together make up molecules and compounds. Molecules are the smallest particle of a substance that retains all of its properties. Okay, that sounded a bit confusing. What does that mean? Well, basically, molecules are things that no matter which one you take, it has the same properties. So, for example, if we're buying cookies, right? If we're buying chocolate chip cookies, this store's cookies are gonna be different than another store's cookies. And, if we go to this bakery or that bakery, they're all gonna be different. Well, the opposite happens with molecules. Molecules, no matter which one you get, it's gonna have the same properties. So for example, if I were to grab a molecule of water, let's say, from here from Florida, and I were to examine its properties. And then if I were to go overseas to Europe or Asia or Africa, and I were to grab another molecule of water, they would have the same properties. So they're made up of two or more atoms, missing a more there, held together by a chemical bond. And we're actually going to be talking about those bonds. They're pretty fascinating. And then compounds are special types of molecules formed by two or more different types of atoms. So let's look at some examples. We have oxygen. This is the breathable oxygen. You know, it's O2. It has two oxygen atoms. And this is considered a molecule, but not a compound, because for a compound, we need, let me highlight it, two or more different types of atoms. And as we can see, you know, here we have two of the same type, so that's not a compound, but it is a molecule. Water's formula is H2O, so here we have two hydrogen atoms and one oxygen atom, and that makes up one molecule of water. So this is a molecule, but it's also a compound because it has two different types of atoms. We have here the hydrogen atoms and also the oxygen atom. Then we have table salt, which is NaCl, so it has one atom of sodium and one atom of chloride. And again, this is both a molecule and a compound. You can kind of see the chemical bond right there. And then we have carbon dioxide, CO2, which has one carbon atom and two oxygen atoms. Again, also a molecule and also a compound. By the way, don't worry if you're looking at these letters and you're like, well, how did we get sodium from Na? That just comes with practice, and I'll be, telling you what the names are for all of the atoms that we need in this course. So don't worry about it. So here's just a quickly review. We have here an atom, and atoms are negative electrons surrounding a nucleus with positive protons and neutral neutrons. Then atoms make elements. Elements make molecules, and molecules and compounds make up just all matter, which is basically just everything around us. We're also going to be briefly going over physical versus chemical changes because this is pretty important to chemistry as well. Physical changes is a change in the physical properties of a substance. So you're not changing the substance itself. You're not changing the molecules. You're not making new compounds. You're just changing the physical properties. Versus a chemical change, one substance is transformed into one or more substances. Okay, so why do we need to know this? Well, this is important because in chemical changes, a chemical reaction is happening. While in physical changes, there is no chemical reaction. This is, pretty straightforward to see because chemical changes are called chemical, so they involve a chemical reaction. So let's look at some examples of both of them. Well, a physical change, changing the physical properties, can happen if you change, for example, the size. So if you were to cut a piece of paper, it's still paper. It still has the same properties of paper. It's not changed. It's not going to behave differently if, for example, you put it in water. It's still going to kind of, get soggy. Or if you change the shape, for example, if you were to crush a can or if you were to break a window or something, the metal of the can and the glass of the window, they're still going to behave in the same way. They're not going to change their chemical properties. You didn't make something new, so that's just a physical change. And also, this is a tricky one, but phase changes. So if you're going from solid to liquid to gas, or, gas to liquid, any of that, like ice to water or water to water vapor, this is not a chemical change. Even though it might seem like we're making new substances, we're actually not, because we're just increasing or decreasing in energy. If you were to grab an ice cube and you melt it into water and then you put it back in the freezer, it's going to become ice again. And this is actually a really good way to tell if something is a physical change, if it's reversible. So for example, again, we can have ice to water and then water to ice. Now, not all physical changes are reversible. For example, if you were to cut a piece of paper, you can't uncut it. But if it is reversible, chances are it's going to be a physical change. Chemical changes, which occur through chemical reactions, are nearly impossible to reverse. So again, if you can reverse something, physical change. They can cause a color change or emit heat or light. So that's kind of one of the ways we tell, oh, did a chemical change happen? Well, you know, if it's emitting heat or light, or if the color is changing, then probably. They happen on a molecular level. They change the way the molecules, you know, the atoms are bonded in a molecule. They break chemical bonds and they create new chemical bonds. And so some examples of this are cooking an egg, which again, you know, we're adding heat to it and the egg is, the white of the egg is changing color. And we can't just, you know, it's unreversible. You can't uncook an egg. Then also burning wood, pretty much anytime you add heat to something, there's gonna be a chemical change. So, you know, again, with the cooking and the burning. And also rusting iron. That's actually a reaction of the iron with oxygen in the air. So that's, you know, pretty interesting and also unreversible. So that's one of the hints that it's a chemical change. So now we're just going to do a bit of practice of physical or chemical changes. In the live lessons, you know, you'd be invited to put a thumbs up if you thought it was a physical change, or put a clapping emoji if you thought it was a chemical change. But for now, if you want, just pause the video and write down your guesses. All right. So number one is breaking glass. Now, when you think of breaking glass, the properties of the glass itself aren't going to be changed. Like, it's changing shape, but it's not changing substance. You're not creating something new. So breaking glass is definitely a physical change. I'm just gonna write it here next to them. Okay, then baking a cake. Well, if you're baking a cake, you're adding heat to it. And for me, you know, I would think, well, you can't unbake a cake. You can't undo it. So I would have to say that's a chemical change. The digestion of food in your stomach. Well, this happens due to, you know, acids, and as I've mentioned before, there are chemical reactions taking place. You know, you're breaking some of the bonds in the molecules of your food and creating new ones. And also it's unreversible, so also definitely a chemical change. Burning plastic. Well, pretty much burning anything is a chemical change because you can't reverse it and you are creating new substances. So like, for example, instead of plastic, after you burn it, you're gonna have ashes and maybe some, you know, air that kind of floats away, so you can't really see that. Crumpling a piece of paper. Well, again, if you crumple up a piece of paper, it's still gonna be paper. It's not gonna change properties. And also you can uncrumple the piece of paper. So that would be a physical change. All you're doing is changing the kind of shape. You know, you're not changing the substances themselves. A lake freezing over. Well, this was a bit of a tricky one because it's a phase change. But remember how I said that all phase changes are physical changes, because all it's doing is going from liquid to solid. So it's going from water to ice. So this is a physical change. And one way that I like to kind of think of this is that both physical change and phase change start with a pH. So whenever you see a phase change going from, you know, gas to liquid, or liquid to solid, or any of that, it's going to be a physical change. A bicycle rusting. Well, remember that we said that rust is iron reacting with the air. So that's a chemical reaction. So that would be a chemical change. Also, you know, it's irreversible, so chemical change. And boiling water is just another phase change, like a lake freezing over, so it's going to be physical change. And if you have any other examples of physical or chemical changes, feel free to drop them in the comments. All right, now we're getting into the periodic table. So you've probably heard of it. It's pretty famous, you know, and it's so famous because it's really useful if you know how to use it, of course. So first, we're going to be looking at all of the boxes. So if you can kind of see, this is basically just various boxes arranged in a pattern. Every element that exists, or well, every element that we know exists, has its own little box. So every one of these is an element. I can, show you some off the top of my head. This is hydrogen, helium, carbon, nitrogen, oxygen, phosphorus, magnesium, sodium, potassium, etc. So basically, if we know that an element exists, it is found somewhere on this periodic table. Okay, so it's organized in a pattern, obviously. Like, this is intentional. Scientists didn't just, grab boxes and were like, oh, let's just throw them somewhere. Going from left to right, the number of subatomic particles, remember those are electrons, protons, and neutrons, increases. So here we have, it's very small, so you probably can't see, but here we have a number 1 for hydrogen. So that means that it has 1 electron, 1 proton, and 1 neutron, as we previously saw. But as we go this way, as we go from left to right, then we find helium, which is 2. So it's going to have 2 electrons, 2 protons, and 2 neutrons. And then, if we go back here, we have 3, 4, 5, 6, 7, 8, 9, 10, et cetera, et cetera. So as you go kind of this way, the number of subatomic particles increases. And going up and down, elements have similar properties. So for example, these are the halogens. They're really reactive. These are the noble gases. We're going to talk about them soon. These are the alkalines. They are really, really reactive and sometimes explode in water. So that's exciting. And then, of course, we need to be able to learn how to read the boxes themselves. So we kind of have 3, sometimes 4 key parts. Sometimes you'll see that the element name is there, sometimes it's not, but in this case it is, and it's carbon. Then we have the atomic number. Now the atomic number is what I was talking about. It shows you how many protons, neutrons, and electrons an element has, and as you go this way, it increases. So here the atomic number is 6. So carbon has 6 protons, 6 electrons, and 6 neutrons if it's not, if it hasn't reacted with anything. Then we have the chemical symbol. So that's just 1 or 2 letters used to identify elements. Carbon's is C. And then we saw that hydrogen's was H. And, we'll be looking at some other ones later on. And then we have also atomic mass. We're not going to be really using it in this class, but it's basically how much an atom weighs. Sometimes it's used in math calculations, but we can find the atomic mass here. If it has, a decimal points and, a really specific number, like it's not just 6, it's 12.011, then it's the atomic mass. But again, in this course, we're not going to be really looking at that. So here are some elements that you might recognize. Here is hydrogen. It's found in water, in hydrogen gas, and a lot of things. This is sodium. It's found in table salt, and it explodes in water, so that's pretty cool, I think. Well, pure sodium, not table salt. Salt is not going to explode in water, just clarifying that. Then here we have carbon. It's found in carbon dioxide. It's found in carbohydrates, proteins. It's in a lot of places. Oxygen, pretty famous. We can't survive without it. And also it's found in water, so pretty cool. And this is chloride. It's a poisonous gas. And if it combines with the explosive metal, then we get table salt. So I think, that kind of shows why I think chem is magic so much, because, we grab the explosive metal, we grab poisonous gas, we put them together, and then we eat it every day, and we're fine, because chemical properties really change after chemical reactions. All right, so now we finally get to talking about the famous noble gases. They're found here on the very, very last column of the periodic table. It starts with helium, neon, argon, krypton, xenon, radon, etc. And why are they called the noble gases? Well, first of all, they're gases, so that kind of, you can kind of see where they get the name gases from. And they're really, really stable. They don't react very much. Now, they're really cool. They're like the coolest elements on the periodic table. All the other elements kind of want to be like them, right? So they wake up every morning and they say, wow, today I want to be like noble gases. Look at them. They have crowns. They're really cool. So what does the coolness of the noble gases have to do with why chemical reactions happen? Well, the noble gases are so cool because they have a full electron shell. What does this mean? Well, remember that there's a nucleus, and then electrons kind of orbit around the nucleus because the negative electrons are attracted to the positive protons in the nucleus. Well, electrons kind of organize themselves in layers or shells, as you can see here. So basically what happens is, if this is the nucleus right here, and there's a K in there because this is potassium, K is the symbol. So this is the nucleus, right? And it has a bunch of protons and a bunch of neutrons. Then we count the shells like this, kind of from the closest to the nucleus to the farthest. Oh, that's a very messy too. But the closest one is shell 1, the second furthest one is shell 2, then this shell would be shell 3, etc. Every shell can hold electrons, right? But it has kind of a limit. So the first shell can hold up to 2 electrons. So we see here 1 and 2. So that shell is full. And then most of the other shells can hold 8 electrons. Oh, I kind of missed one. Sorry, this is supposed to be shell 3. Okay, I'm just gonna stop with the numbers because this is very messy, but I do have them labeled further on, so you'll be able to see. So again, the first shell can hold 2 electrons, and then the outer shells can usually hold 8, right? So we have 1, 2, then you have 1, 2, 3, 4, 5, 6, 7, 8, and then on shell 3, 1, 2, 3, 4, 5, 6, 7, 8. So those shells are full. But then if we look at shell number 4, it only has 1 electron. So that one is not full. It could hold 7 more. Electrons on the very outer shell are called valence electrons, right? So this electron right here would be the valence electron. It's just a fancy term we give them, And basically, the noble gases are so special because they have a full electron shell. This makes them really stable. So instead of having, 1 valence electron like potassium does, all of the noble gases have 8. Except for helium, which has 2. But again, that's a full shell. So basically, noble gases, full electron shells, that makes them really stable, and all of the other elements want to be stable like them. The noble gases don't react very much because the more stable you are, the less you react. And that's why they kind of stick to themselves. Okay, so everybody wants to be like the noble gases. How do we make that happen? I mean, if you're, for example, potassium and you have 1 electron in your outer shell, it seems kind of complicated to just become a noble gas, but elements can actually change to be like the noble gases by gaining or losing electrons. So let's take fluorine, for example. Fluorine, I put the box here. I found it over here. You can see I've circled it. So that's fluorine, and it has 9 electrons. So this is a model of an atom where you can kind of fill up all of these layers. Like this is their capacities. Like layer 1 can only hold 2, then layer 2 can hold 8, etc. So we're just going to draw fluorine. I'm going to put, oh, you can't really see that. I'm going to put an F in the center. That's the nucleus. And I'm putting an F because the element for fluorine is F. And it has 9 electrons because we can see here this 9. Oh. All right, well, this 9. So it's going to have 1 here. Then that makes 2. And we've already filled up the first shell. Then we have 3, 4, 5, 6, 7, 8, and 9. All right, so this is basically an atom of fluorine where you can see that the purple dots are the electrons that it has. Now, shell 3, we're just going to kind of ignore it because You know, if there are no electrons in a shell, we kind of just pretend it's not there. It kind of goes away. But, you know, we have this empty spot where fluorine does not have an electron. And so, as you can see, fluorine is not a noble gas. It's almost a noble gas. You know, it's pretty close to them. If it had 10 electrons, it would be a noble gas, but it has 9, so it's not. But what can happen is it can gain an electron. So let's say that this green electron is not fluorine's, right? It's just kind of there. It's another atom's. And fluorine kind of goes, hey, you know what? I will take that electron. I want that electron. I want to get a new one. So then it comes over here, and you can see that it wasn't fluorine's originally, but now it is. It's a different color, but like now it's in fluorine's electron cloud. And if it gains an electron, it will go from having 9 over here to having 10 over here. And it will become like neon. It won't become neon, you know, there's no actual, we're not going to switch it on the periodic table. But this particular atom of fluorine is going to become like neon, which is a noble gas. You know, we can see neon right here. It's the one covered up by the green. Fluorine with 1 extra electron, which is F minus, F because it's the symbol, is now like the noble gases. So now it's happy. You know, now it can join the exclusive club because since it got an extra electron, it looks like the noble gases and it is stable. It is cool. It is happy and satisfied with its life. Oh, and a quick note, I said that fluorine with 1 extra electron was F minus because it has an extra negative charge. It used to have 9 protons and 9 electrons. That would be 9 pluses, 9 minuses. They cancel each other out. But now it has 9 protons and 10 electrons. Since it has an extra electron, it has an extra negative charge. So it has an overall charge of -1. So we can actually see the number of valence electrons, which remember we said that valence electrons were the electrons on the outer shell. So that's where everybody wants to have 8. We can tell how many they have by where they are on the periodic table. So if you find an element here, it's going to have 1 valence electron. So 1 electron on its outer shell. If it's found here, it's going to have 2. If it's found here, it's going to have 3, 4, 5, 6, 7, and 8, etc. Remember, we want to get to 8. We want to be like the noble gases. So this is kind of where all the elements want to be. Disclaimer, helium, which is right here, is going to be kind of special because it only has 2 valence electrons, but it is happy with 2. Because remember how the first shell only holds 2. So helium, even though it doesn't have 8, it has 2. It's still a noble gas because it's still happy because it has a full electron shell. Kind of like, you know, its outer shell is full, I mean. All right, so now let's take another example. Sodium, which is Na, that's the symbol. So we can see the box here, and I took it from here. All right, so let's draw sodium. So we can kind of see that I'm putting the Na in the nucleus because that's, you know, it has 11 protons and 11 neutrons, but I'm not going to draw them all. Then it has 11 electrons as well before it's reacted with anything. So I'm just going to draw them kind of. It's going to have 1, 2. Then we filled up the first shell. We go to 2, 3, 4, 5, 6, 7, 8, 9, 10. We have filled up shell 2. So now we're going to go to shell 3. And since it's 11, we only need 1 more. So 11. So this is an atom of sodium. And we can see that, you know, it would be like a noble gas because if it didn't have this 1 electron, it would have a full outer shell. But it does have that 1 electron. So it's not a noble gas. It's actually it's in the super reactive row, which is why I said it explodes in water because it's really reactive. All right, so there's 2 ways that we can kind of get this to noble gas status. We can either somehow try to find enough electrons to fill 1, 2, 3, 4, 5, 6, 7 spots and fill up shell 3. So it would kind of go 1, 2. Oh yeah, well, we're just kind of ignoring these in the middle for now because they're called the D block transition metals, and they're really weird. So we're just gonna, they are on the periodic table, but for this course, we're just gonna kind of ignore them for now. So anyways, if sodium were to gain 7, it would go 1, 2, 3, 4, 5, 6, 7, and it would become like argon, which is right here. But I don't know, that's a bit complicated. Gaining 7 electrons, like we saw how hard it was for fluorine to gain 1. Now a sodium is gonna have to find 7, or there's actually an easier way. All that we need to do is grab this electron and get rid of it. If it doesn't exist, and sodium loses an electron, it goes from having 11 electrons to having 10 electrons, like neon. And that is actually going to make it like a noble gas. So without this 1 electron, here, let me try to make this a bit neater. Right, if it has this 1 electron, but then the electron, oh, just want to erase. But then this electron goes away, right? Let's just leave it here for now. And we don't have it anymore. Then it has a full outer shell, and it's happy, and it's like a noble gas. So it's cool. When sodium loses an electron, it becomes Na+, because we still have the 11 protons in the middle, but now it has 10 electrons. So since it has an extra proton, it has an extra positive charge. By the way, even though we can lose or gain electrons, the protons and neutrons pretty much just stay in the nucleus. They don't leave, it's not like somebody can lose a proton or gain a proton. That just doesn't happen in regular conditions. So, if it has 11 protons and 11 electrons, it's not going to lose protons, it's not going to gain protons, it's just going to rearrange and kind of lose and gain electrons. Oh. And now we're just going to do a quick practice. So make your guesses, or, figure it out, hopefully. Will the element gain electrons or lose electrons to become like a noble gas? Here's a periodic table. And remember, the electrons will go to the closest noble gas. So if they're kind of on this row, they might find it more convenient to lose electrons. If they're over here, they find it more convenient to gain electrons. And so yeah, just pause the video and try to figure it out, and then I'll go over it. All right, so first one is chlorine. Chlorine is right here. We've talked about it before. It's the poisonous gas that makes salts. And so we're looking, right? It can either gain 1 electron to become like argon, or it can lose 1, 2, 3, 4, remember we skipped the middle, 5, 6, 7 electrons to become like neon. So, well, chlorine is just going to find it easier to go to argon because it's closer. So this one is going to lose electrons. Let me see if I can write. Oh, okay, that's not pretty. Okay. Or here. All right, there we go. And now we have lithium. Lithium is right here. So it can either gain a lot of electrons to become like neon, or it can lose 1 to become like helium. Oh, sorry. For this one, I meant gain. It's going to gain 1 electron, become like argon. Yeah, sorry about that. I didn't mean gain. Chlorine is going to gain electrons. Lithium, on the other hand, is going to go backwards and lose electrons because it's closer to helium than it is to argon. All right, great. So next one is iodine. Iodine is right here. It's in the same column as chlorine. And it can either lose a lot of electrons to become like krypton, or it can conveniently gain 1 and become like xenon, which is a noble gas. So it is going to find it more convenient to gain electrons because it's closer to xenon than it is to krypton. All right, and now we start getting into kind of the more difficult elements. We have phosphorus. This one's not as obvious because it's not gonna just gain one or lose one, it's gonna gain or lose multiple electrons. So it can either gain 1, 2, 3 electrons, gain 3 and become like argon, or it can lose 1, 2, 3, 4, 5 to become like neon. And well, you know, 3 is less than 5, so it's gonna just pick the convenient route and gain 3 to become like argon. So this one is actually going to gain 3. And then we have calcium, which is right over here. Going to the other side of the periodic table now. It's here. I don't know if you can see that very well. And it's either going to lose 1, 2 electrons and become like argon, or it is going to gain, remember, we're skipping the middle. So you can just jump over 1, 2, 3, 4, 5, 6 electrons to become like krypton. Well, losing 2 sounds a lot easier than gaining 6. So calcium is going to lose 2. And I know that something people ask a lot is, well, what about these? Let me pick green. Oh, is it not? Oh, forgot to set it to draw, sorry. What about this column? Because let's take carbon, for example, right? It has 4 valence electrons. We can tell because we go 1, 2, skip the middle, 3, 4. So it can either 1, 2, 3 gain 4, or it can 1, 2, 3, 4 lose 4. You know, like, so which way is it gonna go? Well, the short answer is it can go either, but usually it doesn't lose or gain electrons, it shares electrons in what we call covalent bonding, but you know, we're gonna talk about that more later. So basically, if it's in, if it has 4 valence electrons, it gains 4 or it loses 4, depending on what's around it. For example, if carbon is around a lot of fluorine and fluorine wants to gain electrons, then carbon will lose electrons because losing 4 around fluorine is easier than gaining 4. And if it's around a lot of lithium, for example, and lithium wants to lose electrons, it will gain 4 because losing in that, gaining in that scenario is easier than losing. So these can go either way. All right, well, that was it for this video. Stay tuned for day 1, part 2 of Intro to Chemistry and Cookies, and hopefully you enjoyed it.